Okay, so yesterday, talking about polygons, just to reiterate, polygons have to be created with just segments. Each segment has to intersect two other segments, and it does it at each other's endpoints. No curves, figure has to be closed, and all segments have to be coplanar. Okay. We've dealt with the smallest polygon possible, which is a triangle. We've dealt with that for a while. Some polygons are convex, some are concave. Convex means that if we extend the sides, for instance, this one here, if I extend all the sides like that, and like that, and so if we extend those sides and none of those sides pass through the inside of the polygon is convex. And we want convex polygons for this course, okay? Those are the ones that we're going to investigate the most. For the mere fact that there's a lot of nice relationships that we can recognize and deal with convex polygons. On the same hand, it's because when we deal with a concave polygon, so a concave polygon, one of those, and it's actually going to be at least two of those lines will pass through the inside. So it'll look something like this one here or this one. These are convex, meaning this angle right here is what usually gets referred to as a reflex or reflexive angle, which means it's greater than 180 degrees, okay? Which is something that we haven't talked about yet, right? Okay, so that's maybe another reason why at this juncture in the course, we want convex polygons, okay? A lot of our theorems and definitions and formulas are going to require convex, okay? So you're going to see, like this theorem here, we talked about yesterday, finding the sum of the interior angles of a convex polygon is n minus 2 times 1/8, okay? Not necessarily the same when we deal with a concave polygon. Where was it?
The cafeteria.
Well, I was waiting for you.
It's really awkward because I just walked up and I was like, that's mine. And he goes, okay.
All right, so yesterday we said, so when we want to determine the number of degrees in a polygon, so let's say that I've got that polygon there, okay? And I want to figure out how much do all of these angles here add up to. We take the formula n minus 2, okay? And what n minus 2 does is it's really calculating the number of triangles that are created when I connect non-consecutive vertices with these diagonals. And that minus 2, essentially, if you think about it, it's the removal of those two consecutive vertices from this one, okay? Because that cannot be considered a diagonal and that cannot be considered a diagonal, okay? If I were to connect that vertex to all the vertices, it would be 5, right? But because I can't connect to consecutive ones to create a diagonal, it's actually 5 minus 2, or in this case 3. Sorry, 6 minus 2. So n minus 2, that tells me how many of these triangles can be created. So there's 4 of them in this case. And then we multiply by how many degrees there are in one triangle. So I get 4 triangles times 180 degrees. So in this case, there'd be 720 degrees in all of these angles that add up to give me that hexagon in this case. Does that make sense to everybody? Okay, so that is the stuff that we talked about yesterday. Now, when we left yesterday, I had a website and it wasn't functioning the way I wanted it to, so let's see if it functions now. Big demonstrates the idea of, you guys can't see it. So this applet demonstrates the idea of creating exterior angles in a polygon, okay? And we've done this with triangles before, okay? we can move and create all kinds of different angles that we want to, all different kinds of triangles. But it's extending one of these sides to create an exterior angle, okay? What this allows us to do is also demonstrate that there's actually, at every vertex, there's actually two exterior angles, but they are going to be vertical to one another, right? So a lot of times we only talk about one of them, okay? We can either talk about the ones that we're moving in a kind of counterclockwise rotation, or the ones that are going in a clockwise rotation. Okay, I think this eventually starts to look like a pinwheel, doesn't it? That kind of makes sense, especially if we make it regular. So I'm just going to look at one of them going clockwise, and let's go with, how many sides we got? 6 sides here. What it does is it calculates what all of these angles are, okay, using essentially a protractor idea in the background. And it's calculating these angles to be these 6 angles right there, okay? And you can see that they total 360, correct? And as I move those angles, you can see that as I move that vertex, it changes 3 of those angles. If I move this one, it changes 3 of those angles. Move this one, changes 3. So I can change them, but what happens to this sum? Stays the same, right? So what that's showing me right now is that a hexagon, as long as the hexagon, the exterior angles with one exterior angle per vertex is going to add to 360. Okay? And that we could prove that pretty easily by just looking at the interior angles and knowing that the interior angles, these all have to be supplementary. This interior and exterior angle have to be supplementary. And these interior angles all total, in this case, it's what, 720? So we could go through a little bit of proof that to guarantee that this is always going to be 360 for a hexagon. But if I add a side, now I got a heptagon, so 7 sides, and we see then with those 7 angles, we still add up to 360. Add more sides, 360. More sides, 360. Now this applet does provide the ability to talk about concave polygons with this, but you see here this 81, which is that it's really not, I don't want to consider it an exterior angle. It's created the same way. The exterior angles are by going from a vertex to another vertex, but continuing through. It says that that's 81 degrees, but it's red. You see what they do with the red one. They subtract it, right? And it still adds up to, I'm not going to ever give you one like that, but it would be, it does still fit this condition. We like to, a lot of times, talk about regular polygons. Okay, so if I do that, okay, we've got 9-sided. Okay, if you remember, that was called an aneagon yesterday. We keep adding sides. What does this, if I don't change the size of the overall shape, so I don't like make it bigger like that, right? So just kind of keep it confined inside. Let's just say we're gonna keep it confined inside this like light peach box here, okay? If I keep adding more and more sides, I guess that's, every time I do that, so it's not gonna get outside of, let's see here. As long as I keep my shape from growing outside of that red box. The more and more sides that I add, so right now, obviously we start with a triangle, right? The more and more sides that I add, what does that shape start to look like? Starts to be circular, right? How many degrees are there in a circle? 360, okay? And eventually, if I'm able to get 360 sides on this thing, which I don't think I can, you would see that each one of these exterior angles is 1 degree, okay? And that might then be somewhat of a connection for us to realize and remember how many degrees there are for exterior angles of a polygon. 360. No matter what the shape is, they're all going to add up. You see here, it's 103 times 3.5 degrees gives me 360 degrees. Okay, does that make sense to everybody? So 360 is that exterior angle sum. So we're going to use that to help us answer some questions here that maybe we weren't able to answer after yesterday's class. All right, here it says, what is measure angle 1 in the regular octagon at the right? Okay, so a couple things here vocabulary-wise that we need to know. First thing is that it says regular. What does regular mean? Equilateral and equal angular. And for us in this problem, because we're dealing with an angle, I'm just going to write here that we know it's equiangular. Okay, that's what we're getting. But regular means that's equiangular and equilateral. Okay. Octagon, another vocabulary word. Octagon means what? 8 sides. Okay. And because we're talking about angles, it also means 8 angles. Okay. Well, we've got it says measure of angle 1. Measure of angle 1. Angle 1 is what kind of angle? It's an exterior angle, right? So if I'm dealing with exterior angles here, how many degrees should exterior angles of an octagon add up to? Yeah, the total is 360. That's the theorem that we just investigated. Okay? Well, if all of them are going to add up to 360, but all of them are the same, how do I find what one of them is? 360 divided by 8. Does that give me, so that's going to go 4, 2, 40, so that's 45? Is that okay with everybody? So what would one interior angle be? If that's 45, doesn't this angle right here, what's the relationship? It's got to be supplementary, so it's got to be 135, right? And let's see if that's confirmed. Yesterday we said for a regular octagon, we could use the formula n minus 2 times 180 divided by n. I'm just going to, for purposes of just getting through this a little bit quicker, kind of cheat here. If I got the formula n minus 2 times 180 divided by n, and n is 8, do I get 135? That makes sense? Okay, yes?
How do you start the octagon way? Like, 135 and then 8.
Okay, so if they tell you got 135 degrees on an interior angle, they want to know how many sides there are? Okay, so that's the next question. All right, so here, and there's two, I'll show you 2 different ways of doing this. And you're going to find out that one of the ways is predominantly much quicker and easier. But I'm going to first target this with the direct way, because it talks about an interior angle, right? So the direct way with dealing with an interior angle, and it should say if you have we can't do this if the polygon is not regular, okay? So I say if you have a polygon with one interior angle equal 150, I need to say if you have a regular polygon, okay? Because I have to have the assumption that they're all the same. So because we have a formula for that. One polygon or one interior angle of a regular polygon is always found by taking that formula. So this 150 is found by taking that there. N minus 2 times 180 over n should equal 150. Okay. Now, because we have one variable in here, we can solve this. This is a rational equation, but it's not all that difficult to solve. And what you're going to find out is that this process is very repetitive. So in the next question, if they ask me if that 150 changes to 135, it's the exact same steps to solve. Okay, it's the exact same multiplication, all that kind of stuff. If you have an equation that has a denominator, if we have fractions, you always want to get rid of that denominator as fast as you can, right? And the way you do that is you multiply by the least common denominator. Okay? So my least common denominator, look up here, what's my denominators are n and 1, right? So my least common denominator is just n. So I multiply both sides by n, so they'll cancel here. I'll multiply by n over here. So it gives me n minus 2 left over on the left times 180 equals 150n. Next thing we have to do because we got n's on both sides now, we need to manipulate this so all your n's show up on one side. In order to do that effectively, we actually need to distribute here. So we get 180n minus 360 equals 150n. And what you realize here, hopefully, is that if we're going to do this problem later on, the only thing that really matters, or that is from problem to problem, when the 150 changes, is the 150. The 180n minus 360 will always be in the problem. Okay? So some people say, Mr. Fay, you said we have to start here. But after we do 3 or 4 or 5 of these, we realize that we can always maybe start there instead. Does that make sense? Because you're always going to multiply both sides by n, and you're always going to distribute that 180. Okay? And then you're always going to subtract this 180n from both sides. So I get negative 360 divided by, or equal to negative 30n. Okay, and right there, it's not as obvious, okay, to what we're going to do in a moment, the shortcut to this, but some people say, or can realize that they can always start there if they wanted to, instead of starting up here with this formula, okay? This is not as easy, but if I look at this 30n, how does 30 compare to 150? It's the what do I get if I add those two together? I get 180, right? So 30 is the what of 150? It's the supplement, isn't it? And that might maybe trigger something here in a moment. But if they're both negative, can I take 360 equals 30 now? If they're both negative? And then how do I solve for n? Divide both sides by 30. So in this case, 30. I always divide 36 by 3 gives me 12, right? So if they asked me to name it, in this case, it's a dodecagon. Sometimes it'll be okay just to say it's a 12-gon. I think on questions like this, they probably, if it has a name that is common, like dodecagon or octagon or something like that, there'll probably be a drop-down window or something like that, or a bubble will fill in. But that's how you can do it. That's one way you can do it, okay? And that's using the direct method, using the formula of an individual interior angle of a regular polygon, okay? I refer to it as the direct technique because that's exactly what they're talking about here, okay? An indirect method would be to use the exterior angle. If I know this is a regular polygon, and it's an I don't know the number of sides yet, so starting this problem fresh, I know that one interior angle is 150. So again, I don't know how many sides I have, but the way I kind of do things is no matter how many sides I have on my figure, can I always zoom in? If I got 12 sides, can I always zoom in to have something that looks like 3 or 4 segments just kind of looking like that pattern right there? Does that kind of make sense? So I'm not going to draw the whole figure because I don't know what the whole figure is. I don't know how many sides I have, but I know no matter whether I have 12 sides or 8 sides or 5 sides or 6 sides or whatever, I'm going to have segments that come together like that in some fashion, right? Does that make sense? Okay. Now, I don't know what it does everywhere else, okay? But I know it does something like this, zoomed in on that section, okay? They're saying one interior angle is 150, right? What is, if one interior angle is 150, what is one of these exterior angles here? 30, right? Does that make sense? Okay. Now, if this is a regular convex polygon, it doesn't even have to be regular. This is true for all convex polygons. What do all of the angles add up to? All of the exterior angles add up to? They add up to 360, right? We know because this one's regular, if they all add up to 360, they all also have to be the same, right? So if I have, how many times do I have to add 30 to itself to get 360? Well, the answer to that is division, isn't it? Take 360 divided by that exterior angle of 30, which is exactly what we did right there, correct? Okay, so that last step of the direct method actually confirms or argues the logic of this. Take 360 divided by that exterior angle, and it gives you right away that 12 that you need. So my argument is, guys, you are going to be so much more efficient and so much more successful at just taking, when they say 150, say, nope, I'm not going to deal with the interior angle, I'm going to deal with the exterior, I'm going to deal with the supplement. Take 360 divided by its supplement, and that will give you the number of sides you got. So in the next question here, it says 144. Okay, so 144. So what is the, so if that's 144, what is the supplement to 144? 36. Okay, so 36. So if that's 36, then all of these have to be 36. And they all need to add to 360, right? But they need to add to 360, but they're all 36. Doesn't that mean there will be 10 of them that I'm going to have to add together? So if there's 10 angles, that would be a decagon. Does that kind of make sense on how to do those things? Were those the questions that you had from your homework that? Let me know which ones, so we can put them up here. Does anybody have like direct questions right now about any of the material or content before we go over homework questions? All right.
Like number 11 and 12.
11 and 12. 6.1.
We might have got those things. Hang on, I think I might. Oh, okay.
You good?
Yeah.
Does anybody want to do 11 or 12 or? Does anybody have any questions about anything right now? All right, I'm going to let you use the remaining time to finish up any of that assignment, and there's also some outstanding assignments from chapter 5 that are open until the 14th. If you want to use this time to kind of work on those as well. Remember, those are, I'm going to give you completion points, 10 out of 10 for doing them. So it does not make sense not to do them, okay? If you could come across any questions over 6.1 as you work on that homework, let me know, and I can work with you.